of the Sophisticated Analytical Instrumentation Facility, popularly called as SAIA, was set up in 1974 under a Memorandum of Understanding with the Department of Science and Technology.
In the first 1 or 2 years, there were reports saying that this is something which is unthinkable, that you are giving a professor an equipment which is expensive and he is giving 60% of it to outsiders. So a sharing philosophy.
The basic mandate behind the entire facility was that advanced characterization facilities should be made available to the entire region, the academia in particular, at a nominal cost.
Many of the modern machines are so expensive, it cannot be given to every institution. So even 1 or 2 centers having really sophisticated equipment will now be able to share it with corners of the country where scientists are there, ideas are there.
Hi, good evening, everyone. This is Eli from the Office of Global Engagement, Indian Institute of Technology, Madras. This is my pleasure to welcome all you for the 21st webinar from the IRIS webinar series. And today's the project that we are going to discuss about is millimeter and microwave metamaterials. This project is led by Professor Krishnamurthy CV. He is the professor from Department of Physics, Indian Institute of Technology, Madras. His current research interests include structure and dynamics of fluids under confinement transport through membranes, developing diagnostic tools for non-destructive evaluation involving ultrasonics and electromagnetic waves, design and development of metamaterials for acoustics, elastics, electromagnetic wave manipulations. His ongoing collaborative activities include polycrystalline effects on elastic properties and thermal transport, modular dynamics, FEM hybrid models of grain boundaries, designing and developing electromagnetic non-destructive techniques for level measurement and material characterization at high temperature. He has publications in about 100 peer-reviewed journals. He has been involved in about 40 projects, and he has also been part of development of 3 projects. He has 1 US patent and 1 Indian patent. He is also the co-recipient of the prestigious DRDO Academy Excellence Award for outstanding and internationally recognized contribution in the field of NDT. And Professor Shankar Balasubramaniam from Computer Science Department, Michigan State University, USA, has joined as a moderator today. He is also the University Distinguished Professor and Associate Chair for Research. His research interests include all aspects of computational electromagnetics and electromagnetic wave propagation in complex media. He is a senior member of the IEEE and a full member of the United States National Committee for the International Union for Radio Science Commission B. It's really my privilege to introduce the speaker and the moderator. Before we begin, notes to the participants, kindly use the Q&A box to put your questions and upload the questions that interest so that the moderator can pick up the question and answer it. Now over to you, Professor CV Krishnamurthy. Thank you.
Thank you. Thank you very much. I should thank upfront all the organizers who have made this possible for us to reach out to all these people. And let me begin by sharing the screen. So this research topic, millimeter and microwave materials, is a research program that we are embarking on as part of the Institute of Eminence initiative at IIT Madras. And we are 4 of us. I will introduce the members a little later. I would like to welcome on behalf of the team to this overview of what we plan to do under this research program. So the research initiative essentially combines 3 different nearly standalone research areas by themselves. We are trying to combine these 3 to build metamaterials for various applications. And we would like to focus on millimeter and microwave applications. So the 3 different distinct aspects involved in this are the computational electromagnetics, without which the design aspect doesn't get completed. And we would like to use novel materials in this process. And we would like to involve additive manufacturing as one of the advanced techniques that can help realize the kind of designs that one can come up with this in metamaterials. So when we look at these three coming together, there are two ways by which we can look at it. One is there is this design aspect, which involves some knowledge of novel materials and a good grasp of computational electromagnetics. And then there is this other aspect, which in knowledge of novel materials and knowledge of additive manufacturing, which helps to fabricate the design that has come up through this computational aspects, and then putting them together to build metamaterials for application. So this is the kind of approach that we would like to take. And the kind of scope that we are envisaging in this research program involving metamaterials is to have these metamaterials for different kinds of applications. So we have grouped them in this manner. We would like to have collimators, lenses, and reflectors, which are coming under this beam shaping feature. We would like to have polarizers, which can be used as discriminators and rotators. We would like to develop absorbers, which can help us in EMI shielding and energy harvesting as well. And we would like to develop some sensors involving building of antennas and bolometers, all of which are essentially based on metamaterials. So this is the scope which we are thinking of achieving in the next few years. If you were to look at metamaterials and ask what are they, one of the ways to look at it is to say that these are materials where whose electromagnetic properties can be designed by us. It's completely an engineered material, and to understand it in a broad perspective, there is this material parameter space that I have shown you here, where you will see that there are two characteristic parameters that define electromagnetic properties of a material, that is the relative permittivity and the relative permeability, epsilon and mu. You notice that it has been drawn here. Over 4 quadrants, you will find there are 4 possible values that these permittivities and permeabilities can take. This is a very general picture. Now, what we are familiar with is the first quadrant, where the epsilon, the relative, both parameters are positive and giving rise to a refractive index which is positive, and which implies that this material is transparent when an electromagnetic wave passes through this. And most of us are familiar with these transparent materials, and these are also called dielectrics or insulators. If you look at the second quadrant, where the relative permittivity is negative, we see that it has this characteristic that it becomes transparent only above a certain frequency. At lower frequencies, because of this negative value for the relative permittivity, the waves that enter into this medium die out. So that is what is indicated by this damped oscillatory feature on the left, which tells us that it's opaque at those frequencies. Many metals come under this category. And if you look at this fourth quadrant, we again find the relative permeability becoming negative. And again, as for the second quadrant, you will find that it is transparent above a certain frequency. It is opaque below this. And here, some of the magnetic materials come under the picture. So these are basically naturally occurring materials, all the three that we have just now discussed. But when you look at the third quadrant, there's a very unusual feature here, where we look at the possibility that the relative permittivity and relative permeability both becoming negative. And this is also transparent, but these materials are not found in nature. And this is where the idea of designing materials from natural materials can be thought of, and we will see how this can be done. There's one other aspect, which is this region near the origin, where you will find many interesting phenomena taking place because the refractive index is nearly either 0 or nearly 0. Basically, it means that the relative permittivity and relative permeability both are nearly 0. So we will look at a feature, some of the features of these consequences of these values. So if you look at the metamaterial from a slightly different perspective, we can think of it as basically built up of meta atoms. These building blocks are different from the normal atoms. So we know that the normal solids can be built up by atoms or molecules. Now we would like to think of a structure built of some building block, which is itself some complex metal. It could be a spherical shaped or rod shaped metals, or it could be dielectrics of complex shapes. It could be hybrids of metal and dielectrics. So you will find one of this illustration here talking about some kind of a ring-like structure that you see there, which is also known as plasmonic resonator. So if this becomes the building block, we end up having this entire material behaving like a metamaterial. And the way it handles electromagnetic waves can be understood from the Huygens principle, which tells us that each one of these building blocks can be viewed as a secondary source excited by the primary wave, and then it starts radiating. So this collective behavior of the secondary radiated wave fronts constitute the new wave that comes out of this metamaterial, exhibiting very interesting properties, which are not found in regular solids, naturally occurring solids. We can go more than this. We can go further by looking at what if we make this building block an active material or as a nonlinear material. The possibilities that we can have in controlling the electromagnetic waves behavior is tremendous the moment we make this active. So which means that almost every element or every building block is controlled in some fashion. And we can go further and look for a possibility where we can actually think of reconfigurable metamaterials. So this is just one illustration that is shown here, where we can adjust the phases or control the phases of the material, of the wave that reflects off this material through applying some specific voltages to every element. So there is this possibility of making this reconfigurable. I can change the pattern by which I'm exciting it. So these are all the possibilities that one can imagine. And most of this have been slowly getting realized through intensive research across the world. A huge number of or explosion of papers have come about exploring all these possibilities to various degrees. Now, what does it mean to say that there's a metamaterial for the microwave and millimeter wave regimes? So if you look at this, this cartoon here, it tells us that there's one way of looking at, there's a scale that we would like to introduce here. One is the natural free space wavelength, and the other is the size of the particle that makes up, that is the building blocks size. So if this, and it's the ratio R is what we are looking at here, which is the free space wavelength by the typical characteristic size of the building block. So if the value of R decides in which regime we are in. So if you notice for metamaterials and metasurfaces, R value is of the order of 10, or maybe starting from 3 onwards, it goes off to 10. And if you look at what it means specifically in terms of the microwave and millimeter wave, you can look at the scale that is given below or bottom left, which tells us that we are working somewhere between about 30 centimeter wavelength to about a millimeter or so, if we go all the way to millimeter waves. So over this range of wavelengths, we would like to have objects. So when we define the application for a certain microwave regime, the wavelength gets fixed, and then we choose the structure, the building block, to be less than that, so that the R value is high. And so then we realize this metamaterial. There is also one regime which is coming under what is called as photonic crystals, for which the R value lies between 1 and 2. These are also, we can call this as one other aspect of metamaterials. If Usually the metamaterials, when you look at the picture that I had shown you earlier, they were periodic arrangements of the building blocks. So if the period is adjusted such that this R value lies between 1 and 2, we end up having a photonic crystal. I mean, the name is different. So the kind of properties that you get are different for photonic crystals as compared to metamaterials. And the color scheme tells us that there's a metal involved in this and there's a dielectric. It's a combination of metal and dielectric in all the applications that we look at. And if you were to look at the metamaterial in this context, in the context of microwave and millimeter wave, we look at the parameter space again and see that the negative metamaterial, the epsilon negative metamaterials can be realized by having an array of rods, metal rods, and an array of mu negative metamaterials. I mean, mu negative metamaterials can be obtained from an array of this resonators, split ring resonators. And if you combine these two, epsilon negative materials and epsilon mu negative materials, you get up the third quadrant, which is a combination of these two, where both are negative and you have this negative refractive index material formed, the material which does not exist in nature. Now, what can these metamaterials do? There are many things, very surprising features associated with this metamaterial, the way it handles the electromagnetic wave. So the first panel that you see here, on the left, you see what we normally associate with the response of a normal looking lens to an electromagnetic wave. So we have a plane wave falling on a lens, and this lens it partly reflects the incident wave and partly transmits it. And the way it transmits it is that it focuses onto the point, and we realize something called a focusing effect. And these features, typically these are many wavelengths thick, the lens material, and you notice that it is curved. The basic refractive index is homogeneous inside it, but the surface is curved. But what if I want to imagine or make a material, which is this metamaterial, which is flat and the thickness is either lambda or less than lambda, but have this material properties, have some spatial dependence, which is basically making it inhomogeneous. So inside this flat region, the epsilon and mu will be spatially dependent. So if you were to imagine such a material, we see this a simulation where we have a slab with a source very close to the slab, where you see the source radiating waves, and the transmitted waves have become plane. So we are realizing plane wavefronts coming through, transmitted by this thin slab, designed to do this job. But you notice the kind of values that we are ending up with. These values are something that you will never be able to find in natural media. The value ranges are given on the right. You will find that we can't realize this. You also notice one other thing, that the source, the radiation coming from the source is not getting reflected from the slab. It just goes in and becomes or transformed into a plane wave. So all this has been made possible by transforming the material properties inside the medium in a very complex manner, making it inhomogeneous, and we have this range. Now, how do we realize this range is where this range of values with using real materials is the challenge. I shall talk about this in the next few slides. Before I continue to proceed to other features, there are other three features that I would like you to know of what can happen if there is negative refraction that we can conceive of in a metamaterial. You will notice that in the lower left bottom, you find the second slab having this negative refractive feature where the rays are fanning out from the source, but they converge into the source because of negative refraction, unlike the normal Snell's law behavior that is associated with the positive refractive index. And then it diverges again and then comes back and gets focused outside. Not only that, the evanescent wave, which is the waves that are not normally propagated through the medium and outside, because they get attenuated rapidly in the medium. They all do not get attenuated. They try to come through the system or the slab and come out as well. So we find that literally all the waves that have been released from the source, which is sitting outside on the left, will be we'll be able to gather all this waves back at the outside or at the output side. So this is a consequence of negative refraction. And this is another aspect where objects can be surrounded by materials which are metamaterials. So the inside sphere is an object that we would like to conceal or hide, so to say, from the wave perspective. So we enclose this object by material, which is a metamaterial. The metamaterial behaves in such a way that the wave that goes in, you will see the ray trajectory is shown there. They all kind of bend around the object and go past it outside. So for an observer on the far side, there is no indication that the wave has got scattered from any object. So to the observer, the object is concealed. So they will not know about it. So this is one aspect that is made possible by the choice of the metamaterial. And when you come to near zero refractive index, you will notice that a very strange thing happens, that wave fronts which are shown on the left, which have some feature, undulating feature, become planar wave fronts and takes on the shape of the outgoing, the surface feature, that is the exiting surface feature. That's because of the way the refractive index modifies the ray. It's a simple ray picture, but the point is that this feature allows us to conceive of certain applications which cannot be again realized in nature. So what I have shown you here is all the possibilities or what can be thought of. Now we have to see how this can be realized in real life. There's one other aspect that I would like to touch upon. This is to do with the absorbing feature of a metamaterial. We are familiar with natural absorbers. The natural absorbers have lossy features which will make the incident wave get absorbed. But we can make a better design of the absorber so that we can reduce the reflection that takes place in a normal absorber. And also it can help us realize this absorption phenomenon taking place in a shorter spatial domain. So it can be thin. In fact, it can be made flexible, the material, and and have a very good absorption feature. Now, absorbers, of course, we know that can be used in various industries and in very many places. So it's a very crucial region where we can contribute through the metamaterial design. We can also do something more with an absorber. Instead of, usually this energy gets lost in the medium as heat. But what if it is possible to use this energy that is stored in the material, in the metamaterial, and later on getting harvested? So this is an application that has been very exciting. And this requires the absorber to be having you can see that there are the features that are involved in this is fairly complex. So it should have a wide bandwidth. That means several frequencies should be getting absorbed. It should have a large acceptance angle. It should try to collect waves coming from all angles. It should be insensitive to the polarization because the incident wave can come in different polarizations, for which you need the antenna that collects this radiation should be a very good antenna, very efficient. And all this will be made possible if I have some circuits which can be printed in a miniaturized fashion and attached or embedded in this metamaterial, which will then realize this harvesting of energy from the incident wave. So how do we go about designing metamaterials? We have the modeling and simulation tools. I have listed a few of them here. We can have a mix and match of these tools. So you see that all these tools provide us slightly different capabilities of what can be done with a designing aspect. So if we have an idea about the material and the structure, that is given the natural material, when I say given material, we are talking about regular material that we are familiar with, and we conceive of some structure and we ask what will be the electromagnetic response of this material in a particular structure. So we can use this full wave simulation to give us an idea about how it is. We could also go with geometric optics approximation, which I have shown you earlier, where a ray behavior is thought of, which is a little easier to think of inside and outside the medium. And then given the ray behavior, you can ask what should be the refractive index, or given the refractive index, which is inhomogeneous, we can think of how the ray behavior would be. You could also look at it from lumped circuits, circuit models built with lumped elements, where we can predict the voltage and currents inside this circuits. And then we move on to describe or predict the radiative characteristics separately. We have this transformative optics, which was given as an example to you earlier when we talked about the thin slab, which was trying to generate plane waves. There, we saw the range of values for epsilon and mu. They are basically effective values. And the way we got that was we demanded that a spherical wavefront or a circular wavefront gets transformed to a plane wavefront. If I make this as my condition, I end up having a set of values for epsilon and mu. And this is coming about from using this approach of transformative optics. So with this, I will be able to get this value that I want to have. But again, as I said, there's one other step to realize it in real life. We have to see how this effective values of epsilon and mu can come about. And there's yet another way to look at it using the effective medium approach, where we are given the material and the structure, we can try to predict what would be the effective values of epsilon and mu. So you see that each one of them gives us a certain way of looking at it, and we can combine or mix these approaches to get the kind of response that we are looking for. Now, we can also go, you realize that this process of choosing materials and choosing the structure involves some iteration. We realize that once we have a structure, it may not be the correct structure. We may see the output slightly different from what we had thought of, the output response. So we would like to come back and redesign it. We might like to change the parameters, a slight spacing change or slightly the shape change can be done. But this process is a very laborious process if we were to do it manually. So there is, people have tried to optimize this process through various ways. And what is given here as deep learning is one way of looking at it. Under that, you can think of using different approaches, neural networks, genetic algorithms. There are many schemes by which one can try to optimize the iteration that is necessary to get at the correct structure in a reasonable time. Otherwise, it takes a long time because there are very many things that we are trying to optimize in this. And we can also ask a very interesting question where we have the output and we would like to know what the input should be in order to realize this output. This is called the inverse problem and is a little more tougher than the problem that is posed on the top panel, where the input geometry is given and parameters, the material parameters are given and you predict the output. But here, the output is known. It's as if you measured something and you would like to infer what made this possible. So this also will help us understand what is going on inside the medium. So these are the advances that have been made, and that is as far as the design is concerned. But how are metamaterials made in the context of electromagnetic regime? One of the ways which has been found to be very useful is this additive manufacturing technology. While it is possible in principle, or you can do even without additive manufacturing certain structures, it is turning out to be most useful when we employ additive manufacturing technologies. In the context of millimeter and microwave regime, I have indicated here the maximum part size that one can realize using some of these commonly used additive manufacturing technologies. And you will see the resolution also indicated here. You will see that by and large, most of the microwave regime is covered by all these processes. And a little bit of millimeter wave is also getting covered in this. So by and large, we will be using these techniques. Some of these, it can be a mix and match, but some of these techniques would be used in order to realize the structures. Now, this additive manufacturing has several advantages. Why it has become very attractive is this, that it can realize complex 3D geometries. That's the most important aspect of it. And we can do prototyping very quickly. That is, I can realize a structure very quickly by using this additive as a real structure coming out of into my hands to perform some experiments. So this is the turnaround time from a design to get to a structure is very small. So it can be automated, it can be customized, and we can alter the design in real time as the printing takes place. And all this can be achieved at reduced costs. So these are the advantages associated with additive manufacturing, and some examples are indicated to give you some idea of what has been done. And it's left to our imagination now to realize far more complex structures. Now, that's the second act. We started discussing the design aspect and then the additive manufacturing aspect of how to fabricate it. And then we come to this role of materials. And how are these materials going to play a role in this exercise? So we realized that there are certain things that we would like to control through the choice of materials. By materials, I mean the real materials, not the metamaterials. These real materials, it's basically some metals, some dielectrics, and some combinations of this. So we need to make sure that we get the right material. So what are we trying to do? We are trying to control the penetration depth of when an electromagnetic wave hits a metal or metallic or conducting layer. There's a partial transmission. It penetrates a little bit. We would like to ensure that the penetration depth is minimum. Otherwise, it becomes lossy. So we would like to create complex surface currents by having a design. Lateral designs and 3D designs must be such that complex surface current loops must be created. Pathways must be constructed through geometry. And so the material has to be amenable for this. And we should achieve impedance matching. That is, you realize when a wave falls on an object, it partially gets reflected. But if you don't want that reflection, we want to match the impedance of this material with the free space and let this wave go in without any reflection. In order to do that, we need, again, materials, proper choice of materials. For polarization control, again, we require the materials to be chosen carefully. Once we choose these materials, we need to ensure that they are suitable or friendly with additive manufacturing process. Because additive manufacturing requires a powder form or a liquid form, as you saw earlier in the previous slide. We need it in some specific ways by which we can ensure that additive manufacturing process takes place smoothly and continuously. For this to happen, we need materials to be suitable or prepared in such a way that they are amenable for this kind of process. So there must be some ease of fabrication of these materials, and we should choose materials which are flexible, which allows flexibility and also have less weight. We would like to have it compact, and we would like to have the whole thing as cost effective. These are basically very challenging requirements, but that's the point, that we would like to engage ourselves into doing these things and come to features where we can have wide acceptance angle of incidence. We have a wide band or selectivity of this band, and we would like to have sub-wavelength thickness so that it is thin and compact. A typical workflow would look like this. Once we choose a material, we would like to go for a design, have a performance simulation, go for a fabrication, and go for a testing and evaluation. And once that is through, we end up having a prototype. But you realize that, as I mentioned earlier, there are iterative processes. So you see the blue arrows indicating how we need to get back between two of these or any two of this. You will see the testing and evaluation is related to performance and simulation. You see the component design related to fabrication. It's also that the fabrication has to be related to material selection. We have to choose all these things carefully such that we get the right material with the right performance characteristics. Now, where are we? This is, though the reference here is 2011, it has actually captured in the essence of where we are now. And where we are now is basically the region on the right, which says hard work, and where we have this applications, devices, and systems. So what this means is most of the initial work has been done. That is, people have been able to realize some of these things that we have just now discussed: negative refractive index, control, having flexible thin subwavelength structures. All these have been absorbers with fairly good efficiency. All these have been realized in different ways and in different regimes. People have been working not just in millimeter or microwaves. There have been the huge quantum of work that is going on in optics. So across the entire electromagnetic spectrum, a lot of development has taken place. So where we are now is that we have some idea about this now. We just have to go ahead and start making specific systems or devices for various applications. And that is how we are also pitching it. We would like to make use of the existing resources that are available with us and knowledge base that is available. And we would like to move on with this applications. The current team, we have Professor Subramaniam from the physics department at IIT Madras, and Professor Shankar Balasubramaniam from Michigan State University, and Professor Prem Chahal, also from Michigan State University. We four of us are currently in this team. There are 3 PhD students currently working on slightly different aspects of metamaterials, and we plan to expand this team. And the way we would like to go forward in this research initiative is this: that we realize that it's basically a knowledge-based approach, and it is multidisciplinary in nature. It has applications across spanning a large electromagnetic spectrum, and there's a lot of customization that is required across different user communities. So keeping this in mind, we would like to have a resource build-up with a lot of manpower getting trained through our initiative by various collaborative efforts with not only the academic institutions, but also with interested industries. We would like to invite various industries to attend our workshops and conferences that we'll be planning. We also have 2 cells through which we interact with the DRDO and ISRO. We would plan to leverage this collaborative ventures through the cells. We would like to also initiate a collaborative effort with the Institute of Plasma Research, where a lot of applications are required. We would like to apply for various funding agencies through which we can realize some funds. And a very attractive feature is that there is a very active environment at the IIT Madras Research Park, where many startup ventures have become very successful. And we would like to see that the students who get trained under this initiative end up with some starting as startup ventures, and we would like to support them, and they in turn, we hope they would go out and support the industries and various other agencies. So this is the plan. And the opportunities for participation in this program can be like this. The students can come to us for internships or term projects. Project associates we will be recruiting them for short-term and medium-term tasks. We would like to invite faculty from various academic institutions to have joint PhD programs with us. And the kind of tasks that we would like to deal with are split into 4 categories. We realize that there are many things that can be done. The modeling and simulation can be an activity. Optimization alone can be an activity because it's fairly complex and requires different skills. We can work with materials. We can work in testing and evaluation. Each one of them is fairly rich in itself and offers plenty of opportunities for people to work in. And the information and updates about all the activities that we would be planning will be currently, you can view this link that is given at the bottom. We will soon have a separate website created for this research initiative, but currently you can look at this website to look for updates and additional information. Thank you for your attention.
So thank you, Professor Krishnamurthy. To those who are listening, there are a number of questions that have already been asked, a number of questions that have been answered. I see 23 answers to questions. So if you have any questions, please post them and I'll go through it in some reasonably random order, right? So let's start with something that can be that's simple, and then we'll build up to something that's perhaps a little more complicated. So anybody on the panel, when Professor Krishnamurthy, this is, I guess, to you, what is band selectability? Okay. I think it was there in one of your slides. If you could just elaborate on that a bit.
Yeah, so when you, I'll just go to the slide.
Yeah, please do.
So if you notice the bottom left section, you will find that there are wavelengths indicated, frequencies indicated, and at the bottommost part, there are some band designations given: ultra high frequency, UHF, SHF, and EHF. And there are some standard designations associated with these bands. So what we mean by band selectivity is that if I were to develop a metamaterial which is capable of working in 8 to 10 gigahertz or 8 to 12 gigahertz, which is normally called as X band, I would like to know whether I can design metamaterials for a lower band or a higher band. So that is the band selectivity that we are talking about.
Okay, perhaps an even simpler question. I think there are a number of questions that relate to how students can enroll, how students can participate in the program. I think if you don't mind just showing the last slide, I think, or the second last slide, right? So people who have asked this question, if you can take down this slide information.
Is this the one?
Yes, that one. I think you can get all the data from physics at iitm.ac.in, and this particular link should essentially help.
Yes, that's correct.
Okay.
And the email IDs of our email IDs are also there, so they can contact us as well.
Mm-hmm. So let me go to something just building up a little more. I think you discussed something about acceptance angle when you were talking about energy harvesting. If you don't mind elaborating just a little bit on that, so that people can understand what you're talking about.
Yeah. So when we talk about absorption or an absorber, for instance, we would like to know what happens. So the simplest way to realize an absorber is I have a plane wave coming in one direction, now basically a normal incidence, let us say. This is the absorber. I have a normally incident electromagnetic wave, and I would like to see that getting absorbed as much as is possible. But what if I want to have what if an electromagnetic wave is coming at an oblique incidence? So the angle that we are talking about is this, the angle of incidence, the whole range, literally the entire half space, I would say, would be the domain over which the electromagnetic wave can be incident on this absorber. And we realized through the designs that absorbers are not having the same functionality at all incident angles. So that's the reason why we have to put it as a design challenge. We need to be able to design such that all the angles that we would like to have something like this, plus or minus 60 degrees, if I say admittance angle, it means that all waves incident within this angular region will get very well absorbed. Outside that, what happens? It may be absorbed not very well. It could be acting like a poor absorber. But if I have a better design, I can have minus, say, 80 degrees to plus 80 degrees. So I am increasing the angle of acceptance, so to say, where I can admit electromagnetic waves from all these cone of angles and make the absorber work really efficiently for all the angles.
Fantastic. So perhaps something a little more complicated and conceptual, I guess, is what are the current challenges and use of metamaterials for space applications? Are there space applications that one can envision wherein this could be used?
Yes, space applications are being conceived of, and they have been built as well. So the first and foremost challenge is making it lightweight, and that is not easy to achieve. So that's a big challenge, lightweight material, and it should be thin. I mean, the advantage of metamaterial is that it can be made thin over conventional material having the same performance characteristics. So the moment I make it thin, I am also hoping that it can be made lightweight to some extent. But still, the choice of material has to be such that it is really light. So thin materials and lightweight materials are the challenges to get to or cross to make space applicative materials.
Okay, fantastic. So again, this is open to others. This is an interesting question, perhaps, but something that I think we can discuss. How does a design process flow? I mean, in other words, how do, say, lump circuit elements come into play? What is inverse design? So if you could just think about it a little bit, or discuss it, or point people to references, that would be, I think.
References. Okay, I need to dig out the references, but then, okay. So if we look at the, so there is this scheme called the transmission line approach that people are normally familiar with when they deal with lump elements. And it's essentially a one-dimensional structure of a series parallel combination of LCs and Rs. And I launch a wave from one end and see how this wave gets transformed as it propagates through this network of LCR elements or down the line to the output side. So this is something that people who normally deal with electromagnetic behavior follow. And now we want to use the same approach and use metamaterials, or rather, we would like to use the LCRs as the building blocks are the LCRs now. And these LCRs are now going to be having special features. Unlike the normal L and C and R, we would like to have a metamaterial like L, C and R having negative, for instance, negative values are now conceived of now. And so we would like to put those elements in and ask the same question of what happens when an electromagnetic wave propagates through this network of elements which are themselves having complex features. So that's the basic approach under this lumped element circuit model. And the circuit models techniques are already in place. So of course, it's not that it is trivial extension, but the framework is available, so it can be built up upon.
So, so another very interesting question is: are there medical applications for metamaterials?
Yes. So one of the human, okay, when we want to apply it for medicine, particularly for a human body, the shapes of the various parts of our body are having some distinct features. So the immediate thing will be to have a conformal shaped element that will help us transmit or let the electromagnetic wave go into the material. If you want to send electromagnetic waves in to do an inspection, let us say, we would like to, suppose we have an arm, and we would like to know how to send the electromagnetic waves into this arm in an efficient manner. The best thing would be to have a conformal material, a metamaterial which is flexible and which takes on the shape of the surface locally, and then allows this electromagnetic waves to pass into the material and interrogate the medium. And in this process of creating this metamaterial, we also ensure that the impedance is matched. That is, there are no reflections or losses of the incident wave that gets in, and vice versa. That is, the wave that gets scattered back from the insides should come through to me without any loss. So I would like to have an impedance matched conformal surface, which should be a metamaterial to help me interrogate the human part. So this is that's how it has been applied as already. They have already started applying this.
Mm-hmm. So there are some questions that are perhaps a little too deep into theory, and I don't know whether we can address them right off the bat. I think there are a number of the literature on this particular topic is actually very, very vast. It's not small. If you just search in Google Scholar and type metamaterials, you will be inundated with technology that has gone on for almost about a decade or so. So I would ask those who have answered that, asking that kind of questions, to just go there and look at it. So that is there. I think the goal of this would be to answer perhaps a higher level question rather than something much more fundamental. So let's look at something interesting here. So the one question is, why is additive manufacturing preferable? So perhaps if we can go into I think the way to answer this would be to say, how can it be done? What was done before and what can be done now? So I don't know whether you would want to answer it or whether Prem would want to answer it. I think that's
yeah, I would request Professor Prem to take this.
Okay, I guess the key one, as you know, was shown in the slides, that a metamaterial in a sense is composed of a lot of unit cells. You can see that. And each of those unit cells has to be tailored for certain resonant frequency, for example. And in particular, if you want three-dimensional structure, it'll be very hard to fabricate using conventional technique like microfabrication. Microfabrication only allows planar structure. So now we want is three-dimensional structures, which can be done using additive manufacturing. That's one aspect of it. And then the second aspect of it is that now you can embed or mix and match many materials while you're printing in real times. That's one. And also individual unit cells can be tailored to be different from, let's say if you're looking at the center versus to the edge. So that is also easily tailorable. And mixing or matching a material, talking about that is we can mix dielectrics or conductors or even magnetic materials combination. So the beauty is that it opens up a huge design area, or it gives you more freedom to design different things and also to easily fabricate. And another advantage is that most of this additive manufacturing or these 3D printers are very small, and you can have it on your desk, so you can just design and print and test it right there. Rather than going to a clean room. So those are the key advantages. And then also you can print conformal or non-conformal structures. So there are many advantages to using additive manufacturing compared to conventional techniques. And conventional technique has been well studied. So the new frontier is the additive manufacturing for such things. And what we want to do is we want to be able to not only tailor the material at individual cell, but we want to go down at the atomic level and say, can we tailor the material there? So we'll use the conventional material properties. Then we take the advantage of the structure as well. And further, can we bring in active elements in there? So can we tune this individual unit cells in real time? That's another. So it gives you for example, it gives you a design flexibility let's say to design antennas that can have a tunable frequency, or a radar which can you can have broadband radars, which are difficult to do right now. So those are the key advantages, or this is the reason why you want to pursue this.
So there is another question on complex geometry, but I think and how materials is how AM is can help. So, but let me ask CVK to put in the slide on inverse design, and I think that is a good build up to I think this question. So this question is, what exactly is complex geometry, and why is conventional manufacturing difficult? So I think all of this can be viewed from an inverse design perspective. And so, for instance, the fundamentals of inverse design perspective is that you want that as an output, the figure in the extreme right as your output. So the question that you're asking is, given this output, how do I design the layout? And it's not a two-dimensional layout, it's a three-dimensional layout that would give me that particular output. That is really what you're asking. So if you think of three-dimensional design, that is much better done in terms of understanding what the layout is and essentially realizing it using additive manufacturing. Prem, correct me if I'm wrong. Right? I think that will be that essentially opens up a new avenue for research in some sense. Okay. Yeah, so this is an interesting question. For machine learning models to optimize parameters of systems require a lot of data. Are these data sources that will be only simulation results? Anybody want to take a stab at that? That's a very good question.
Can you repeat that, Shankar?
For machine learning models to optimize parameters of a system require a lot of data. So machine learning models require a lot of data in order to optimize anything. What are the data sources? What are the data sources? Are these simulation data sources? Are they others? What does one do? So let me take a stab at it. I think this is there are some very classic inverse design approaches. One of these is by somebody who's very well known in inverse design. His name is Sigmund, and his group has been doing inverse design for a long time. And some of this has been picked up in the metamaterials community fairly recently. Machine learning is one possible avenue for topology optimization, but that doesn't need to be the only possible avenue for topology optimization. And you're right, if I do machine learning, I need lots of data. And machine learning for electromagnetic systems is extremely limited to very simple examples. But there are other approaches to optimizing layouts which use more of derivative information, as done in the inverse design papers that at least I have seen. Okay, and those essentially use gradient-based approaches to figure out what the layer of the material should be, with a lot of success, I may add. Okay, I think we've answered a number of questions. Okay, so this is another interesting question, but somewhat off topic, but I think somewhat pertinent. Can you share mechanical properties of some metamaterials? Is there a correlation between materials, lightweight materials and all of that kind of stuff? Is there something that you guys can talk about?
Not really, but then I can tell that there is a huge research activity for developing acoustic metamaterials, and it's going on. I mean, a lot of work has gone on, and people have realized these structures. And one of my colleagues in the Department of Mechanical Engineering, Prabhu Rajagopal, he has developed some metamaterials for acoustic metamaterials for imaging application, and also a seismic wave absorption. I mean, he has designed metamaterial structures around say a building, such that the seismic wave gets attenuated by this fencing kind of thing, and the building is safe, so to say, or any enclosure that we want to protect. It can be fenced by metamaterials which will damp the earthquake or the seismic waves that come there. So that's one of the kind of things that he has been doing. And people have done lightweight structures which can withstand loads, which don't buckle, using metamaterial. I mean, they have used ideas of origami, the paper folding idea. They have made materials inspired from this origami structures, and are successful in creating metamaterials for structural aspects.
And adding to that one, there is a lot of interest from automotive now For example, people want to build lightweight bumpers which can take the impact and still survive, and different structures within the automobile itself. There's a need, and also there is some interest from tires as well, because they want to have certain patterns so that you reduce noise while you're driving, those kind of aspects. So there is significant interest from automotive in this thing.
Right. So just as a very, very high level, and this, I'm throwing a lot of physics under the bus here, but essentially what I want most of the audience to take away with is that when we're talking about metamaterials, we are talking about material, we're essentially looking at kind of effective properties of materials. We're not going down to the grain level and trying to figure out so we're trying to build it from that level, but essentially trying to figure out how we can build it, construct it such that you realize certain properties at the very end, right? So the properties that we're measuring are end goal properties. And there was a question earlier about why can't nature do this? Well, nature has not had an opportunity to do it. So, right? But I want all of you guys to think of something the next time you see a butterfly, right? If you look at a butterfly and then I want you to ask yourself this question, or any insect, where do the colors in the butterfly wings come from? The answer to that is that it is not due to any pigmentation. It is purely structural, right? In other words, the wings of a butterfly, the wings of any bird that you see that is colorful, essentially it is structure of the wing or of the cellulose that makes it up, that gives you the color, right? So that and different shades of that color. Unfortunately, nature has not had to deal with too many things in the microwave regime. So it's right. Okay, so here's so Prem, is there something that you can think about for piezoelectric metamaterials? I don't know if that is used at all. I mean,
the piezo-based is actually, if you look at some of the piezo materials, they are usually broadband, and if you want to get a high quality factor. So what they do nowadays is that they're trying to combine the natural property of the material, and when I say metamaterial, mostly the geometry. So there's a combination of those two, so you can enhance the quality factor. For example, if you're going to design a filter for something, you need a high quality factor. And so the combination of the piezo, where you basically excite going from electrical to a mechanical, once you are mechanical, can you have the highest quality factor at one, in a sense, resonance? And there is interest from that point of view. I don't know if that's what the question pertains to, but yes. But also related to that, there are certain geometries we can make within, let's say, PDMS, so that you can, absorb or have a higher attenuation, mechanically speaking, using certain structures. So now it's a soft material in addition to the geometry on top of that. So now you can have a broader band type of absorption.
Okay.
Can I add some more to that?
Yes, please.
Yeah, sure.
So when you take this piezo material into the metamaterial system, it is possible to generate or to use that as a kind of energy generation. So you have the piezo material, which also will have the dielectric property, okay, that can be used as a part of the metamaterial structure.
Okay.
Basically, tunable capacitance.
Yes, tunable.
It would become an active metamaterial, isn't it?
Yeah, because it also will have, as a Professor Prem says, if I have any mechanical things on the mechanical force on that, then it also will be generating a kind of an external electric field that can be used to as an activator for that.
Okay.
So you
So
have both the metamaterial EM device plus a tunable nature embedded within that.
Okay, here's an interesting question that I'm going to have a take on. So what are the main advantages? What are the advantages of metamaterials over, say, a radiation absorber, a typical radiation absorber, typical? So is there somebody who can comment on that?
I think Professor Subramaniam can.
Can you please, typical radiation absorber, let's look at. Okay.
Yeah, typical absorber, yeah.
Typical absorber is generally a broadband absorber. It cannot have, or it does not have any tunable nature for that. A metamaterial absorber has the functionality to choose the frequency of radiation that can be absorbed. Certain radiation, what we want, has to be absorbed. Some radiation need not to be absorbed. So these type of functionality can be provided within that. So metamaterial structure with a broadband absorber will be a boon to actually manipulate the frequency at which it can be absorbed greatly. So that is the.
That is one part of it. Yeah, go ahead.
Sorry. I think the example that Shankar gave was pretty good. Like say the butterfly, right? The wing of a butterfly. So it's natural. It's not a natural color, but the color comes because of the patterning. So because you're absorbing certain radiation to get the coloring, right? So that ability to tune that without using the natural material, which may not be available for that frequency range that we are looking for, and that's the beauty. So we can manipulate the properties through geometry rather than looking for a natural material which may not be available.
Right. There are a number of questions that talk about strength of these materials and so on and so forth. I just want to point out to the audience who have these kinds of questions that this particular topic is about electromagnetic properties of materials, right? I mean, so if one of your criteria is strength, then you can actually build it into your design process, right? I mean, so think of it from that perspective. If you want, I mean, you really don't want this to be the main beam in your house, for instance, right? I mean, that doesn't make sense. But if strength is a criteria that it has to be on, say, on a wing of some kind, and you want it, then you can build that. But you want it of a certain shape that you can build that in, right? I mean, so that's something that I think you can think of. Don't view it as a material. It's not a material per se, but it really provides electromagnetic properties. Right. That is really how you should be thinking about it.
Yeah, I mean, I can add just a point here that there are certain applications where we need a good combination of strength, mechanical strength, and electromagnetic performance. Mm-hmm. So that's where, I mean, that's an additional challenge. I mean, naturally, we don't want flimsy electromagnetic devices, flimsy from a mechanical point of view. So it does get into the picture at some point that we need fairly stable, mechanically stable and strong material which performs electromagnetically the way we want it. So
I think it also elaborates to the question related to satellites. Now, let's say you have an antenna. The antenna can be used as a structure mechanically, but also it can be used as an antenna. So how can we hybridize things? And that's what this is leading.
Correct. So this is a little more back to what you were talking about earlier. This is how do EBGs relate to metamaterials? So there's electromagnetic bandgap structures. I think you had a slide.
Yeah. I'll just go back to that.
And that's a question. There is also a question regarding the difference between metamaterial absorber and photonic crystal, or PBG or EBG.
Yeah.
If you take the case of
you could answer both.
For the case of the photonic band structures or photonic crystals, they have the periodicity, or you can see the structure is a slightly huge structure. Okay. There the materials, the individual materials are arranged with a spacing such a way that it is of the order of the lambda. But in the case of the metamaterial, the size of the meta-atom is subwavelength nature. So this is the main difference between the metamaterial and that of the photonic crystal or EBG bandgap structures. Okay. When it comes to the performance wise, both will have a similar type of performances. What all the things metamaterials will say can also be realized by the photonic crystals or photonic band gap structures. Okay. And the another similarity between the two is both will have a very high anisotropic nature, and their band structures will actually define the way the electromagnetic radiation is flowing through. So this is the difference as well as the similarities between the Ebg structures and that of the metamaterials.
Can we say that we can have exclusive photonic crystal based properties which
Yes.
are not
Which are not realizable by metamaterials?
Yeah. If you can say that way, maybe.
Okay. Most of the properties what we realized using photonic crystals, okay, can be realized using metamaterials. In fact, both share the almost similar such features. Okay, both have a different band structure. They have a very good anisotropic natures, etc. So only thing is that for which purpose or which location you are going to use that. In case you are going to use it in optical fibers, I don't put the metamaterial structure. Instead, I use the photonic crystal nature on that. Okay, so it depends on the where I am going to use. Okay, there also selects that. Okay. Otherwise, I can't say that no, what all the things photonic crystal does, other metamaterial will not be able to do. One thing is that I cannot use the photonic crystal as a kind of an absorber for energy or the same, but people can use it for confining the energy and then taking the radiation out. That is possible in photonic crystals. Metamaterials, no, it can be used for because of the planar nature, okay, the size. They are useful for several versatile applications than that of the photonic crystal.
Okay.
So I just want to add one point. In metamaterials, the meta atoms need not be arranged in a periodic way. Whereas for photonic crystal, it is crucial, essential that the building blocks are arranged in a periodic manner.
Right.
So can you elaborate why in that a little bit more? And in terms of frequency application, in terms of regimes of applications, because I think people are asking whether it can be used at higher frequencies, you know, at infrared and so on and so forth.
Yeah, so I mean, when okay, Professor Subramaniam, you want to go at it?
No, because of if you take the case of the higher frequencies, we have the at present, if you see that design consideration may not be a problem, but when it comes to the manufacturing region, okay, we have certain problems associated with that. We say that the case of the additive manufacturing also, if you take it, surface finish becomes a very great criteria. Okay, so these type of things now, as soon as we start answering, we can use the metamaterial for higher frequencies, okay, like in the millimeter wave and higher than that. Okay. But once soon as you cross certain limits, I can always go for the etching, okay, like E-beam evaporation, other things. So we have to use a different kind of methodologies to realize the metamaterial structure. So there is no exact, or you can say that at present, though we have certain problems in the manufacturing methodologies, okay, later I think in future we may be able to surpass that and use these for a full range of frequencies, right from microwave to optical region without any problems.
Okay. So for those who ask that regime of questions, I think the principal takeaway, if you go back to your textbook when you learned about properties of materials, essentially everything was based on a periodic lattice. So obviously, when you want to try and do things, I mean, assuming that they are smaller than the spacing of the lattice is smaller than significantly smaller than the wavelength, and that's essentially what the basic idea here is. There is a complex material, it's arranged in a lattice. And then you figure out what is an effective property. Can you move away from a periodic lattice? Absolutely, you can try it. That's up to you as a designer, right? You can move away from a periodic lattice. and you can transition from a periodic lattice to something slightly different. And then essentially, it comes down to how it interacts with light. When I say light, I mean at all frequencies. I'm not confining myself to optics, right? So that essentially is, so if you want to think of yourself as a designer, that's what you have to play with. Of course, design process can get very complicated because, if I have a bunch of very complicated structures, they're aperiodic, then periodicity makes my life very simple because then I'm just working on the unit cell. The minute I make it aperiodic, then my problems becomes very, very challenging, right? And so as a designer, you're setting up yourself for much more challenges when you go away from simplifying assumptions, right? But that is something that is open to you. There are several questions. There are some questions that there are very specific questions, and I think some of these very specific questions, for instance, can metamaterials be used in solar cells? And I think those are things that you can pretty much Google. So please use Google. That's perhaps our best new crutch or best helper in some sense. And you'll find people have tried doing this kind of ideas for a lot of different applications. Right? Perhaps not EV, but yes, pretty much everything else. Okay. So I think we pretty much answered most of the questions. I think one main thing is there other good books on metamaterials that you can look at? I know of good authors. I don't know of. I know very good authors in this area, and I'm sure they've written books, but I haven't really followed up. I don't know whether you have something off the top of your head, Prem, or CVK or something. Do you guys know of good books?
We can answer many of these questions by email if it is needed, because there are
we can.
30
we can also do one thing. We can put out some resources on our website so that they will be in a position to look at it. We will do that. We can provide links and things like that, specific to certain things.
Yeah. So there are some questions that just don't that don't make sense to me. I don't know whether any of the other guys can look at it. Because there are questions on, there's one word, shielding, that's a question, but I don't know what that means.
Probably he might be meaning about, or like to talk
electromagnetic shielding
through using
what it is?
Aspect.
I don't know, it just says shielding, so I don't know what that means. So can it be used? Yeah, sure.
Yeah, definitely.
Yes.
One of the primary applications.
Yeah.
This shielding can be a tunable shielding. Actually, active metamaterials can be used as a tunable shield. So it's one of the
there are
applications.
Yeah. So there are some others who are asking how does local parameters. So this question is, how can we control the value of parameters by knowing the parameter value? That seems to be very cyclic in terms of the question. But if you know epsilon and mu, if you know the distribution of epsilon and mu, changes in distribution of epsilon and mu locally will affect the response far away. I think that's what it means.
So you can look, maybe the last block here, effective medium approach, is typically the way one proceeds to get the effective parameters given the actual material parameters. Suppose I have copper material in the form of, say, rods and arranged in a particular pattern spatially. And I would like to know what is the effective value of epsilon and mu because of the spatial arrangement of copper rods. This can be arrived at by using this effective medium approach, where the local properties, by local we mean over the scale of the wavelength that we are interested in. We will try to average out the properties coming from or contributed by the currents that are generated from copper rods when they are excited by the incident wave. So this is typically the effective medium approach. How to get effective parameters of a metamaterial given the building blocks, the copper or anything that we know. I suppose that's, yeah.
Yes.
I
So
think there's a
that
lot of
again.
sorry.
Yeah.
I think if you look at some of the questions, there are a lot of confusion between metamaterials and real materials. You know what I mean?
Yes. Okay.
So
okay.
I think if you go back to the slide you had, see that which shows that it's a bunch of unit cells, and each unit cell is a geometry.
This one?
I think that early on you had one, three-dimensional.
Yeah.
This one, like this.
Is this one?
Yeah, I think that's the one, right? Because if you look at the metamaterial, if you look at the center figure, you see a bunch of rings, right? That's a geometry. But when we say metamaterial, it's the effect of all those things put together. When the wave goes through, what does it happen? So we are treating it as an effective medium, but it's not the conventional thinking of material. I think, and there's a lot of confusion from that aspect. Based on some of the questions I'm reading.
Yeah. So what I want people to take away from it is that as you zoom into it, you're looking at it at optical regimes, right? I mean, you're looking at it at very, very high frequency. So you can essentially tell whether this is a ring or this is a small rod or something up to that effect. But suppose the wavelength that you were looking at were much, much larger than the ring. You would not be able to distinguish the ring at all. So imagine that your wavelength is a meter, but the size of the ring is a millimeter. You can't tell that it is, you can't distinguish. So at that point, what the wave sees is a material that it's passing through. The question that we're trying to figure out is that what is the property at that scale? What properties at that scale can be designed using a combination of what does it at higher frequencies is a ring, a rod, arranged in a certain manner, such that you would get an effective epsilon or an effective material property, right? And to answer the last, I think this is the last. This is one of the
and
last
if I can
questions.
add to that, Shankar, easiest way to think is that your screen, right? Like you're looking at the screen. We are not paying attention to individual pixels. We are paying attention to the whole screen. And
that's right. That's a very good example. That's a phenomenally good example, right? So you at this point are not focused on any given screen, any given pixel, right? You see the picture overall, right? Unless the picture quality is so poor, the pixels are huge. So, right?
Yes, that's correct.
Okay, can you guys look at it and see if I'm missing anything from a big picture perspective? So our metamaterials model, considering they're isotropic, they're not. They are essentially, you take details at the scale, at a unit, say, cell scale, and then extract an effective property. And because you're extracting an effective property, they'll look isotropic, right? For a certain frequency regime. So as you go higher and higher in frequency, that assumption, of course, will break down.
I just put up a slide which says this. The slab will have very anisotropic material properties. On the right, I have indicated.
Right.
And I think there's one interesting, nice question is related to absorbers. So it basically, the question relates to that you have energy absorbed, where does it go?
Yeah.
Right. And I think the brief answer is that when you, let's say you absorb RF frequency, let's say RF power, it goes to, it's absorbed, but then it's converted into heat as an example. So now you're, radiating as heat or, transporting the heat energy. So it is going somewhere. It's not just disappears. So you're converting from one to the other. And the structures are helping you do that easier.
And if we don't want to let it go as heat, we can have the energy stored. And then this energy harvesting can be realized.
That's correct. And bolometers are that example. They use that change in that, or you can use you can heat up water, for example. So now you store that energy as a heat in water or something.
Right.
Okay. I think we have pretty much answered the most significant questions here, unless I'm missing something. Do you guys see if you're missing anything significant?
Almost, I think we have answered all. There is also a question on how metamaterials can replace functionally graded material in additive manufacturing technique. That is actually the advantage of the additive manufacturing technique to here the metamaterials can replace functionally graded material. That's what the question is. Actually, the functionally graded material can be replaced metamaterial only by digital means, like you can prepare. But the functionally graded material is one of the important aspects for the transmission variation. Okay, or you can say that conformal methodologies can be used to do that.
So there's another one. Is not the prototype development process limited by capabilities of additive manufacturing techniques? Yeah, I mean, so there is a bottleneck somewhere. It depends on what kind of tool you have, what kind of equipment you have, right? That's how well you can do it. So if you can't print metal, then you can't print metal. But there are people who can print metal. So yes, that is correct.
I think we will put answers for the rest of the things in our website, maybe.
Yeah. So I think we can put answers to some of these on our website, as well as suggestions for books and authors. I think authors are better because you can actually follow their work over time.
I think with this, I think we can close the presentation, right?
I'll just stop sharing. Okay.
Yeah. Thank you, everyone. Thank you, Professor Krishnamurthy. Thank you, Professor V. Subramaniam. Thank you, Professor Shankar Balasubramaniam, for the wonderful session. And we can say the question raised how much people enjoyed the session. Thank you very much. And participants, keep watching the link tree for further webinars from IRE series. Thank you once again.
Thank you.
From our team, we would like to thank again all the participants who stayed through the whole session. I hope you have got something out of it. And as we say, we will be putting up on the website some of the references and resources that you can follow up. And you please feel free to write to us if we want to know more about what is to be done. Thank you.
Thank you, everyone.
Thank you very much.
Bye.
Bye.
Thank you, Professor Prem.
Bye.
Thanks, Prem. Thanks, Shankar.
Bye. Bye, guys.
Bye.